let's start with recalling what we did really in the last discussion, which is really the Stokes theorem. What does Stokes theorem says is that imagine you have a surface, okay, and it's a Stokes surface. By Stokes surface, I mean a surface for which you have a kind of a parameterization which really parameterize this inside region of the surface. But this surface, in addition, also has a curve as a boundary of it. Okay, so the curve has a boundary of it. Okay, and then what really Stokes theorem is saying that if you have, for example, a vector field that is kind of defined over it, okay, over this surface, or it could be defined in the entire region, but I'm just only interested in that part of the vector field which is related or lies on this surface actually. Okay, so imagine on this F I have a vector field defined to every point of this surface. I have a vector associated with it. Okay, so what is the Stokes theorem is telling you that okay, you have this vector field if you, for example, compute the all microscopic curls of this vector field over this entire surface. Okay, entire surface. Okay, in other words, that if you sum up all these microscopic curls of the vector field over the entire surface, this will equal to the total circulation of the F that is happening over the around the boundary of this surface actually. Are you getting the point?
Yes.
So that's really what it says, that okay, you take the local, so you have this vector field F, okay, and you take these local curls, okay, around the surface, and then you sum up all of these local curves over the entire surface actually, then this total what do you call local curves over the sum of the total local curves over the entire surface would be equal to the circulation of F over the entire what do you call boundary of the surface actually. So that's what essentially the circulation of F over the boundary of F. So that's what is really what you call the Stokes theorem. Okay, the mathematical. So what is really? So what was the Green theorem doing? I mean, if you remember, the Green theorem was turning a double integral into a line integral actually, in a way. While this is doing what? Mathematically, it's it's really saying that you have this vector field, okay, which is del cross F. Then its surface integral is really equal to the line integral of F around the C actually. So in other words, in a way, it allows you to compute the surface integral of, for example, a vector field actually. Okay, and it would be much easier if that vector field is curl of something actually. Okay. Anyway, so it's a recipe to convert the surface integrals into the line integrals. So what I would like to do today is that I would like to by the way, there are different versions of it. In other words, for example, in the classical books, what you will see is that okay, this will be written in this form. So del cross F dot ds, and it makes sense actually. So what you are saying that take a small chunk of the surface, okay, and see that how much of the curve is happening in this small chunk of the surface actually, okay, and then sum this all over the entire surface, okay, is equal to take a small chunk of, for example, curve, okay, so it's like a dr is a really small portion of it. And you see that what is the circulation of F in this small, what do you call, chunk of of the boundary of the surface, and then sum this up over the entire, the boundary of the surface, and the both should be equal. So that's just a classical way to write it. Okay, so in some books, for example, the physicists love to write things in this manner. Okay, but essentially it's the same as what we are saying. So there's no difference between both. Okay, so let's do an example.
Sir, what do we mean by circulating around the boundary? So what does it mean by circulating?
Okay, so I mean physically you could mean that, imagine that what is, for example, you can also represent, if you remember, we also talked about that the line integral of f can be interpreted physically as, for example, if f is some force, field that is, for example, that is acting on, for example, this entire surface. So what does this is representing? So this line integral is representing the one work done this by force actually. Okay, so the one way to interpret, this line integral around f should be that, how much of this f is doing work done along the curve. But you can have many kind of interpretations of it. Okay, is it making sense?
Yes.
So let's do an example. So imagine I have a surface. Okay. Imagine I have a surface that looks like this. So that is defined, for example, through a rectangular equation. So z is, say, for example, 5 minus x squared minus what we call y squared. So that's the surface. And I'm interested not in this entire surface, but the part of the surface that is above z equal to 1. Okay. By the way, if you want to picture this in your head, how does this picture is going to look like? So if you want to see the sections of this surface, how does each section would look like? So think about it. So if you fix z equal to 0, so it's a circle centered at origin with the radius 5 actually. How about if you put, for example, z equal to 1?
Circle at point 1.
So it's going to be circle attached to the point z equal to the 1. But what would be the radius of it?
So its radius would be 4, 2.
Okay, so it would be
2.
It would be, so x square plus y square equal to 4.
Square root of 5, sir.
So square root of 4.
Square root of 4 means it's going to be 2 actually.
2,
X square plus, it's going to be,
2.
What do you call a center.
Yes.
So can you think that what is happening actually? So at z equal to 0, you have a bigger circle. Okay. At z equal to 1, you have a relatively smaller circle. So you're gonna really see that what is happening is that you have these number of circles, okay, which are kind of placed on each other and creating a really, what kind of picture is going to create? So it's going to create this kind of a picture. So for example, if you fix it, so it's gonna be not really a coin, but
So like in first case we did paraboloid, but it is the opening upwards, like paraboloid.
It's something like something. Can you see what is happening? Yes. But I mean, if you really want to see it in 3 dimension over this part, so what does this say is that I'm not interested in the part below z equal to 1, but z equal to 1 actually. So at z equal to 1, what it would be? So it's going to be a circle attached to z equal to 2, okay, and then so it's going to have something like this shape, okay. So it's going to be something like this shape actually. So what would be this top value? What do you think? So in other words, at what value it will kind of stop going up?
At 5, sir.
At 5 actually. Think about it. So because if z is 5, then this point is x square plus y square equal to 0. So it's really the origin actually. So there's nothing beyond. So it doesn't make sense above 5 actually. You're getting the point. So that's what is really the surface that we are talking about. So is this a Stokes surface? I'm going to say, yes, it's a surface, you have a parameterization. Does it have a boundary? So what is the boundary of it actually? What's the boundary of it?
Parabola is a three-dimensional.
Not parabola, but it's really this. So in other words, the boundary should be a curve. So this curve actually. So this circle can be treated as the boundary of the curve actually. So this entire surface is really S, and the circle C is really the boundary of the surface actually. And what I would like to do, I would like to compute, okay, the surface integral of this vector field. So the F is defined in this manner. So the F is really, for example, z square minus 3xy and x cube y cube actually. So something like this. Okay. So imagine that I have a vector field all over it, but I'm only interested in that part of the vector field which is kind of associated with this this surface. All right. So what I'm interested in computing the surface integral of the F. Okay? The surface integral of the F actually. Or maybe the surface integral of not F, but surface integral of the curl of the F. Okay. So how can I compute it? I mean, one way is that I just compute it directly. Can I compute it directly? For this, you need to have a parameterization of, what do you call, so what would be the parameterization of it actually?
So U, comma V.
So that's really a Mong patch actually. So
Yes,
this is, so that's really a graph surface. So it's a graph of what? So it's a graph of this function f of xy
Yes, sir, is
equal to 5 minus x square minus z square, where z is really between 1 to 5 actually. So your z is here. Okay. So if you want to write it in the parametric form, so the PUV is going to be
U, comma V.
so it's going to be UV
5 minus
and 5 minus u square and
minus V.
minus v square actually. You getting the point? So what is the restriction on U and V? Can we think about the restriction of U and V? Here's the thing. What would be the projection of it in the two dimension? Because the domain is coming from the two dimension, UV plane actually, huh? X, Y, Z. So what would be that? What would be the image of this? If you see the shadow of it, it would be what?
Circular.
It's going to be a circle, it's going to be a disk actually. So the disk is really the domain of, okay, this picture. So if you are choosing your U's and V's from this disk, you will get, this picture as an image actually. So what would be the restrictions on U and V? So what should I say? So I'm going to say, if U is kind of representing the radius of it, okay, so it's going to be between what?
1 and 5.
No.
No.
So it could be 0, and at max it could go to, at max it could go to the radius of this picture actually. So it could be the 2.
2, sir.
Okay. Like this is something that you have to fetch out of the information. And how about V? So V should be 0 to 2 pi.
Yes, I am.
Because
We
you have to go all around it actually. So it should be really 0 to 2 pi. Okay? And once you know this, you know how to compute this. Is it a difficult thing to compute? Because you just have to do what? You have to do the del cross F, and first you need to compute del cross F, and then you need to substitute this parameterization, P of UV, and then take its dot product with what? The normal vector actually, okay? So how you're going to draw a normal vector to each point from the surface is that you simply compute the PU cross PV actually.
Yes.
Okay, you take the dot product of it, PU cross PV, and then integrate it dV dV. Is it making sense?
Yes.
And then substitute the values. So U that U could between go 0 to 2 and 0 to 2 pi, so I'm not getting into the calculation that how to calculate it. समझ आ रही है बात?
Yes.
So easy peasy stuff actually. Okay, so you have to do a lot of effort, when you want to, because you have to figure out parameterization, you have to figure out, where everything is, so what is the domain for this parameterization, you have to figure out the normal vector, so lots of computation actually. Okay? But what is the blessing of, really Stokes theorem is that you can just get rid of all these calculations and just compute this line integral. Now, if you want to compute this line integral, what you need? You need to know the parameterization of C. That's what the really thing that you need actually. Okay? Because if you know the parameterization of it, you can compute it easily. So what is C? So what is C? So in other words, if I want to write, for example, P of t, so the P of t is what? It's a circle.
Yes.
Attached to the z equal to 1 actually. So what should be the parameterization of P of t?
Sine cos of t.
Sine cos of t.
Cos.
Sin t cos.
अरे भाई सर्किल की पैरामीटराइजेशन क्या होती है?
Sin t cos. R
So
sin
you just have to see r cos theta and r cos. So does this circle, this boundary has a specific radius?
Yes, sir.
What is it?
Two
So it's going to be 2 cos t and 2 sin t and 1. So that's really the parameterization of it is. Okay? And then what can you say about t? So the t runs between 0 to 5. Okay? It's really 0 to 2 pi. Is it making sense? So what are you going to do? Let's just compute it. So I know the recipe to compute the line integral. You need to evaluate f at p of t. In other words, take this stuff and substitute it into your f. Okay, and take the dot product of it with the p prime of t and integrate it dt from where to where? 0 to 2. That's it. Okay. I'm not doing computation. So what would be the meaning of f of p of t? So I know that f acts on x, y, z. So it swallows the 3 numbers and gives you this vector as an outcome actually. So when f would operate on p of t, in other words this, so it's going to swallow these 3 numbers, and what it's going to spit out? So it's going to spit out this vector actually. Okay. So what would be that vector? So the z square is going to be 1, and minus 3xy is going to be what? 3 times 2 times 2, so it's going to be 12. xy is going to be sin t cos t, and then x cube is going to be, you know how to calculate. Okay? So you know how to calculate f of p of t. And then what you need to do, the p prime of t, so I don't need to tell you that how to compute the p prime of t. Okay? Just take the dot product and you get your result. Okay? So do the computation.
सर इस सरफेस की बाउंड्री जो है सर वो z के चेंज होने से वेरी करेगी ना सर?
सरफेस की बाउंड्री,
ये जो हमने पैराबोलिक टाइप शेप का बनाया है सरफेस, इसकी जैसे जैसे हम डिस्क मतलब डिवाइड करें अगर इसको डिस्क में, तो हर एक पोर्शन की बाउंड्री वेरी करेगी ना सर?
Okay, so I'm treating this as a single piece actually. So when you are going to slice it, for example, okay, and you're gonna see, so why you want to slice it actually?
सर मैं स्लाइस नहीं कर रहा, मैं कह रहा हूँ कि सर इसकी बाउंड्री इस पॉइंट पे z इक्वल टू 1 पे मतलब ये होगी इक्वेशन, लेकिन z इक्वल टू 5 पे इसकी बाउंड्री
I don't need to compute the boundary is going to be just 1 actually. So if you are considering I'm considering this surface as a whole above z equal to 1. So it's just going to have a 1 boundary. The other things are going to be the sections of the surface, not the boundary. So those sections could be boundary if you restrict your domain. For example, you can take a, instead of taking z equal to 1, you take z equal to 2 as a section actually. Okay. Then you're ignoring the other part. Okay. Then you're saying that okay, by z equal to 2, you are getting another circle here. that would be a different circle than this. Okay, and I'll treat that circle as a boundary of what you call surface. Okay. So the first thing is really to make sense of surface. Okay. I mean, if you can, for example, I would always suggest when you are solving a practical problem, always plot the surface, and this is easy. You know, just open your GeoGebra and write this as stuff, and it's going to give you the really what do you call required surface. And once you see the surface, you can make sense of it, that why this boundary is really the boundary of what do you call given figure. Is it making sense?
Yes.
Okay. So one example is enough.
Yes.
Okay, good. So there are lots of examples waiting for you in the notes and in the exercises for you to do actually at least solve some of the exercises from the Stokes theorem. Okay. So Stokes theorem works for the surface with the boundaries actually. Okay. So in other words, the Stokes surfaces. While when we define surfaces, our definition does not naturally include boundary in it actually. Okay. It doesn't include boundary on it because the P, the parameterization through which we defined our surface is an open set. So the domain of it is an open set. And the output of it sits in this set. Okay? It's in this set. So if this doesn't contain a boundary and this map is a smooth map, then this, really the P of U is also not going to contain the boundary. So our definition of surface does not explicitly have, so we are talking about the surface, not necessarily with the boundaries. And Stokes surfaces are those surfaces which have boundaries, curves as the boundary actually. Okay, so Stokes theorem is valid there. Alright. Let me just make another picture. Let me just give you, for example, I'll not do the calculation, just to show you another kind of really a surface. So consider okay, so here's the thing. Imagine, so the question demands this. So imagine I have a vector field that goes like this. X squared, y squared, and x. Okay? And the curve, and I have to compute really the line integral of this vector field actually. And the curve that I have been given is this. So the curve is a triangle with the vertices. So it's a triangle, okay? So triangle with vertices as 1, 0, 0, 0, 0, 1, 0, and 0, 0, 1. Okay? Triangle with the vertices this. So if you're going to picture it, how does the picture is going to look like? The picture is going to look like this actually. Okay? So the 1, 0, 0, 1 is here, with the 0, 1, 0, 0 is here, and 0, 0, 1 is here. So I'm talking about this triangle. Okay? So what would be the direct way to compute this integral? The direct way to compute this integral would be that, okay, you treat these three curves as, independent curves and really compute the integral over each of the curve actually. Okay? Compute the integral over each curve.
Yes.
Right?
Yes.
By the way, there is another restriction over about the curve in the Stokes theorem is that the curve should be a closed curve actually. You can't have an open-ended curve actually. Okay? You can't just have a one line. So, it should be a closed curve. So this is really a closed curve. Okay, this is another important thing that we find. Take as you have it. So one way is that, okay, you try to find the line of each of the equation, for example, and I can find it. It's not difficult. I have been given 2 points, so I can find a line that passes through both points. Okay, and then using that equation of line, create a parameterization of each one of what you would call the curve, and then evaluate really the integral over each curve. So that's one recipe of doing it. But what I can treat this problem is that the other way could be that I can treat this as, so this guy as a surface actually. Okay? So I'm talking about this top, what you call rectangular region. So I'm not talking about the thing that is inside that top rectangular region. So I'm talking about this rectangular region actually. Okay? So the other way could be, so this is really a perfect situation where you have a surface S with a boundary, single curve, and that single curve could be what? Just concatenate these 3 curves and you're going to get a curve that can be treated as the boundary of, this surface S actually. And you can, so the Stokes theorem applies. Okay? So the Stokes theorem applies because each part of the boundary is really smooth actually. So when you're going to concatenate them, you're going to get a really smooth boundary. Okay? The good boundary. It doesn't have any problem. So what you can do is that, okay, you want to compute this, so compute the kernel of F over this surface actually. Okay. So compute the kernel of F over this surface. Now the question is, what would be the parameterization of the surface? Because if you want to compute this surface integral, you need parameterization. So what should be there? How can I find the parameterization of it? Any suggestion? What would be the parameterization?
So first we'll find the equations of these lines.
Then
through here 10 lines.
I said you can have a situation where you can even directly attack the problem actually. Think about it. Can I directly attack the problem? So what I need in order to compute this? So I can interpret this as del cross F over this surface, okay? Maybe I can write the domain, okay? I'm going to write it in a minute. Dotted with what? The PU cross PV. But what is PU cross PV? It's a normal vector actually. So you dot this with normal vector. You need to divide this by the magnitude, and du dv. Or maybe if you are, for example, if this is written in the terms of xy, so this is simply dx and dy. Okay. Is it? So where does x varies actually? X और y की variation कहाँ से कहाँ तक?
सर